Somewhere around 15 billion miles from the Sun, at the true edge of our solar system, there's a region of space that physically shouldn't be able to reach the temperatures Voyager 1. What actually measured there? Not according to the models scientists had spent decades building before this spacecraft ever arrived. Interstellar space, by every reasonable theoretical calculation available before 2012, was supposed to be cold, thin, and relatively calm right at the boundary where our Sun's influence finally gives way to the galaxy beyond. Instead, Voyager 1's instruments recorded particles slamming into each other with enough energy to generate temperatures reaching approximately 30,000 degrees Celsius, hot enough that researchers studying the data reached for a name that sounds like it belongs in a description of a dying star rather than the quiet space between stars. They called it a wall of fire. This is the real story of what Voyager 1 actually measured at the true edge of our solar system, why that specific region of space produces temperatures no existing model predicted it should reach. And what NASA's own scientists say this genuinely means for how humanity understands the boundary protecting everything and everyone who has ever lived on Earth. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why finding extreme heat at the edge of our solar system counts as a genuine violation of prior expectations, rather than simply an interesting data point, you first have to understand exactly what scientists believe this specific boundary should look like before Voyager 1 ever measured it directly. For decades before Voyager 1 approached the heliopause, the true edge of our solar system, researchers built careful, peer-reviewed theoretical models describing what a spacecraft crossing that boundary should encounter. These weren't casual guesses. They represented some of the best available work from serious heliophysicists, built on decades of studying the Sun's behavior, the physics of plasma, and everything indirect telescopes and instruments closer to home could tell us about the general character of interstellar space. And the overwhelming consensus of that modeling work predicted something calm. A slow, gradual transition, the solar wind's outward push, thinning out steadily as it lost strength against the pressure of the interstellar medium pressing in from beyond, with the interstellar plasma on the far side becoming gradually more detectable as that transition unfolded. Picture something closer to a river slowly widening and blending into an ocean, rather than any kind of sharp, dramatic, or violent boundary. That is not remotely what Voyager 1 actually found. On August 25, 2012, the spacecraft crossed the heliopause and entered true interstellar space, becoming the first human-made object in history to leave our solar system entirely. And right at that boundary, the particles Voyager 1's instruments detected were not thinning out calmly the way every available model had predicted. They were moving at speeds approaching a meaningful fraction of the speed of light, colliding with each other at energy levels translating to temperatures of approximately 30,000 degrees Celsius. It's worth pausing to actually understand what that number means and why it doesn't work quite the same way temperature does in the environment you're sitting in right now. In the extraordinarily sparse, near-vacuum conditions of interstellar space, temperature isn't measuring something you could feel the way you'd feel heat radiating from a fire or a stovetop. It's a measurement of the velocity and kinetic energy of individual particles, spaced so far apart from each other that there's essentially no meaningful transfer of thermal energy between them the way there would be in the thick, dense atmosphere surrounding you on Earth. But the particles themselves are genuinely moving at those extreme velocities, carrying genuinely extreme kinetic energy, even though the overall density of the region is so low that a spacecraft could pass directly through it without being physically burned or damaged by anything resembling ordinary fire. Some researchers studying the specific data have nonetheless described the region using language that captures the raw physical violence of what's actually happening there, calling it a wall of fire, not as a literal description of flame, but as a genuine, deliberate acknowledgement that this is a real, concentrated zone of extraordinarily energetic charged particles, forming a physical barrier at the very edge of everything our solar system contains. To understand why this temperature reading genuinely broke the standard model, rather than just refining it slightly, you have to understand the specific physical mechanism scientists eventually proposed to explain it. The heliopause isn't simply a passive line where two different environments happen to meet. It's an active boundary where two competing pressure systems, the outward push of our Sun's solar wind and the inward push of the surrounding interstellar medium, are locked in a constant dynamic balance. As particles from both sides pile up and interact directly at that specific boundary, the energy involved in those collisions doesn't dissipate smoothly or gradually the way the older models assumed. It concentrates, compressing into a genuinely violent energetic transition zone, a real physical structure rather than an abstract dividing line on a diagram, and the resulting particle velocities at that specific compression point are exactly what produced the extreme temperature readings Voyager 1's instruments recorded. This wasn't the only piece of Voyager 1's heliopause data that broke prior expectations. And understanding the second major surprise helps explain why researchers describe this entire region as fundamentally more complex and more dynamic than anyone had modeled beforehand. For decades, one of the foundational, widely accepted predictions about crossing the heliopause involved the behavior of magnetic fields on either side of the boundary. The expectation was straightforward. Inside the heliosphere, the sun's own magnetic field, carried outward through space by the solar wind, should point in one specific, consistent direction. Outside the heliosphere, in true interstellar space, the completely separate magnetic field of the wider galaxy should point in its own different direction, with the crossing itself marked by an obvious, measurable shift, as the spacecraft passed from one distinct magnetic environment into the other. Voyager 1 found something categorically different from that expectation. The magnetic fields measured on both sides of the heliopause were, in ways no existing theoretical model had specifically predicted, connected. The sun's own magnetic field lines, carried outward and increasingly compressed as they approached the boundary, were interacting directly with the galactic magnetic field beyond it through a real physical process called magnetic reconnection, where field lines originating from entirely different sources rearrange themselves and release genuine energy in the process, similar in basic mechanism to the physics that drives solar flares on the surface of our own sun, just occurring here at the very edge of our solar system instead. Think carefully about what that finding actually means, because it represents a foundational correction to how physicists understood the basic structural relationship between our solar system and the surrounding galaxy. Our solar system and the wider galaxy are not magnetically separate, cleanly isolated systems, the way decades of prior modeling had generally assumed. At this specific boundary, they are magnetically linked, connected through an active zone where real energy is being continuously exchanged between our home and the wider cosmos beyond it, exactly the kind of dynamic, energetic environment capable of helping to explain the extreme particle temperatures Voyager 1 measured in the same general region. It's worth being precise here about exactly how confident scientists actually were in this specific 2012 crossing, because the confirmation process itself tells you something important about how genuinely difficult this particular measurement turned out to be. Voyager 1's own plasma science instrument, the tool specifically designed to directly and unambiguously measure solar wind density and confirm the exact moment of a heliopause crossing, had actually been damaged years earlier, back in 1980, during the spacecraft's flyby of Saturn. Without that instrument working properly, scientists couldn't rely on a single, clean, direct measurement to immediately confirm the crossing had happened. Instead, researchers had to reconstruct the moment using indirect evidence gathered from Voyager 1's other still-functioning instruments, tracking a sudden, sharp spike in cosmic rays arriving from beyond the solar system, alongside a simultaneous, corresponding drop in particles native to our own solar system. That process took an entire additional year of painstaking analysis before NASA felt genuinely confident enough to officially announce, in September 2013, that the historic crossing had actually occurred back in August of 2012. The confirmation ultimately arrived through a fortunate, almost accidental event, a coronal mass ejection that had erupted from the sun back in March 2012. Finally reached Voyager 1's position in April 2013, and the resulting disturbance in the surrounding plasma allowed the spacecraft's still-functional plasma wave instrument to calculate electron density directly, providing the clean, unambiguous confirmation that the plasma instrument itself could no longer offer. 6 years later, when Voyager 1's twin, Voyager 2, made its own independent crossing of the heliopause. In November 2018, scientists finally had a second, genuinely useful data point to compare against Voyager 1's earlier, harder-won measurements. Voyager 2's own plasma instrument was still fully functional at the time of its crossing, giving researchers their first clean, direct, real-time confirmation of a heliopause crossing, using unambiguous instrument data rather than a year of painstaking indirect reconstruction. And when scientists compared Voyager 2's direct measurements against what Voyager 1 had recorded years earlier, they found additional independent confirmation of just how genuinely strange this boundary region actually is. Voyager 2 measured its own version of unexpectedly high temperatures immediately outside the heliopause, its own version of a magnetic field structure that didn't cleanly match the simple, separated model scientists had originally expected, and further evidence that the heliosphere as a whole behaves less like a smooth, symmetrical, sealed bubble and more like a porous, leaking structure with material from inside our solar system found slipping outward into true interstellar space more than 100 million miles beyond the formal boundary itself. That combined body of evidence, gathered patiently across nearly a decade by two aging spacecraft that were only ever originally designed to survive, roughly 5 years each on a tour past Jupiter and Saturn, represents one of the more significant course corrections in the entire modern history of heliophysics. Scientists had spent decades constructing careful, mathematically rigorous models of what the true edge of our solar system should look like, models. Built entirely from indirect observation, using telescopes and theoretical extrapolation from the relative safety of a solar system, nobody had ever actually physically left before. When an actual physical instrument finally crossed that boundary and measured the real, direct conditions there, it found extreme particle temperatures nobody had predicted, a fundamentally interconnected magnetic environment nobody had expected, and a porous, leaking boundary structure that broke the clean, symmetrical picture nearly every prior model had confidently assumed to be accurate. It's worth being honest and direct about exactly what this discovery does and does not mean for life here on Earth, because that honesty is precisely what separates credible science from an exaggerated headline. None of this data suggests any kind of imminent danger to our planet, and no credible researcher studying this information has ever suggested otherwise. What it does suggest is that our understanding of the specific mechanisms protecting our solar system from the harsher radiation environment of the wider galaxy has been built on assumptions that turned out to be measurably, meaningfully incomplete. The heliopause functions as a genuine shield, deflecting a substantial portion of the most dangerous cosmic radiation, high-energy particles streaming in from distant, long-exploded stars elsewhere in our galaxy, before that radiation ever has the chance to reach the inner solar system, including Earth, at anything close to full strength. If the actual boundary responsible for that protection is genuinely more energetic, more interconnected with the surrounding galaxy, and more structurally complex than any model predicted before Voyager 1 physically measured it, then a genuinely careful, evidence-based reassessment of exactly how that protective shield behaves and holds up over long geological timescales becomes a serious, legitimate scientific priority, rather than an idle academic curiosity. There's also a broader, genuinely important point buried in how this entire discovery unfolded, one worth sitting with, regardless of the specific temperature numbers or magnetic field measurements involved. Every single model describing the heliopause boundary that existed before Voyager 1's actual 2012 crossing had been built entirely from the outside looking in, constructed by extremely capable scientists working from a planet using telescopes, careful mathematics, and rigorous theoretical extrapolation, but never from direct physical measurement taken from within the environment itself. That's simply the nature of doing physics on a region of space no human instrument had ever managed to reach before. And the first instrument humanity ever actually placed directly inside that environment came back and told researchers, unambiguously, that those carefully built models were missing something fundamental, that the true boundary of our solar system is more complex, more dynamic, and more genuinely violent than anything careful indirect observation from Earth had ever managed to predict. This pattern of genuine repeated surprise didn't stop the moment Voyager 1 finished its initial crossing either, and understanding that ongoing pattern helps place the wall of fire discovery in its proper broader context. In the years leading up to the actual 2012 crossing, Voyager 1 had already spent time passing through an earlier equally unpredicted region of space, one NASA's own science team eventually nicknamed a magnetic highway, where the outward velocity of the solar wind had slowed to essentially zero, and where senior researchers like Stamachios Kremigis of the Johns Hopkins Applied Physics Laboratory publicly admitted that existing physics simply had no working model capable of explaining what the spacecraft was actually measuring. Years after the crossing itself in 2020, Voyager 1's magnetometer registered a sudden, unexplained jump in the strength of the surrounding interstellar magnetic field, an event scientists eventually connected to a pressure wave, essentially a piston-like compression effect generated by solar activity years earlier, finally rippling outward and reaching the spacecraft's position in interstellar space. And separate, ongoing research into the persistent plasma emissions Voyager 1 has continued detecting since 2017 has revealed that interstellar space itself carries a continuous, structured hum that no prior model anticipated. Either evidence that the region beyond our solar system is considerably more textured, more dynamic, and more actively evolving than the relatively quiet, uniform environment scientists had assumed it would be for decades before the spacecraft actually arrived there to check. Taken together, this entire body of evidence tells a consistent, honest story about the actual, hard-won limits of theoretical prediction when it comes to genuinely unexplored regions of physical space. Careful, rigorous, peer-reviewed science, built by extremely capable researchers using every available indirect tool, still managed to get significant, specific details about this boundary wrong. Not because the scientists involved were careless, but because no amount of careful theoretical work from a distance can fully substitute for an actual physical instrument sitting directly inside an environment, measuring real conditions in real time. Voyager 1 provided exactly that irreplaceable kind of direct measurement, and the wall of fire finding, alongside the interconnected magnetic fields, the porous leaking boundary, and the persistent unexplained plasma hum, all trace back to the same fundamental lesson. our solar system's true edge behaves in ways genuinely stranger, more energetic, and more dynamically alive than any model built purely from Earth had ever correctly anticipated. NASA never designed Voyager 1's original mission around discovering any of this. Its goals, at launch in 1977, were relatively modest by comparison. Photograph Jupiter and Saturn, gather whatever useful data the mission could manage within a 5-year operational window, and then, according to the original plan, quietly conclude its work sometime around 1981 or 1982. Instead, it kept traveling for decades beyond anyone's original expectations, and when it finally reached a boundary no spacecraft had ever physically crossed before, it delivered a set of findings that forced physicists to fundamentally reconsider assumptions that had stood, essentially unchallenged, for the better part of half a century of careful theoretical work. That is not manufactured drama constructed around a dramatic headline. That is the honest, well-documented, peer-reviewed record of what actually happened when humanity's furthest-reaching spacecraft finally measured the true edge of our solar system directly, rather than merely theorizing about it from the safety of a planet nobody had ever left before. So here is where this genuinely leaves things honestly grounded entirely in published, peer-reviewed research and the direct, on-the-record statements of the scientists who actually studied this data. Voyager 1 crossed into true interstellar space in August 2012 and immediately measured particle temperatures, reaching approximately 30,000 degrees Celsius at the exact boundary separating our solar system from the galaxy beyond, a wall of fire that no prior theoretical model had predicted should exist there at all. It simultaneously detected a genuine physical connection between our sun's magnetic field and the magnetic field of the wider galaxy, evidence of real, ongoing energy exchange at a boundary scientists had long assumed was cleanly, magnetically separated. And in the years since, that same general region has continued producing genuine unexplained surprises, a leaking, porous heliopause, a persistent, structured plasma hum, sudden compression events rippling outward from solar activity years after the fact, each one another honest reminder that the true edge of our solar system remains stranger, more energetic, and more actively alive than any model built entirely from Earth ever managed to correctly predict, right up until an actual spacecraft finally arrived there to check for itself. If this kind of story is what you come here for, one grounded in exactly what NASA's own scientists measured and said, rather than exaggeration, hit subscribe and turn on notifications, because there's clearly more of the real universe left that our models simply haven't fully caught up to yet. Drop a comment telling me whether you think the true edge of our solar system holds any more surprises like this one, and share this with someone who still thinks the boundary of our solar system was already fully understood before Voyager 1 actually got there to measure it directly.